Hi everyone, welcome to week 9. We're going to be converting our framework into a deferred renderer this week in order to allow us to more easily facilitate more and more post-processing effects. So the first thing we're going to do is we're actually going to remove a feature before we move on. So as we talked about a little bit in class, problem with deferred rendering is that the handling of components that have transparency is a little bit more difficult. And I don't know if we're going to have the time to by the end, but I don't want to tackle that problem just yet anyways. So we're going to be removing the particle effects first. But other than that, the scene is going to be identical, except it's going to be rendered with a deferred renderer. So before we move on, since we cleared the two particle effects here, let's clean up the rest in game.cpp. So we can take off the fog effect and the sparkle effect here in the initialization. We won't need them anymore in the update. Pretty much everywhere on the right here that we see errors pop up. Right, so here we are with generating the scene, render all our objects, and then here we have a particle program. Oh yeah, we should remove that too. And we have rendering our particle effects here. So let's remove this stuff. And then textures already. Let's move this texture line up a couple so that it stays with this block. Looks a bit neater. There we go. Now, like I said, I forgot. Let's remove the particle program as well here from game.h. Follow through to where it's being loaded, and we can get rid of that sucker. So if we run the scene now, it should work just fine. Now the first step in creating a deferred renderer is creating the G buffer, creating the buffer holding all the textures that comprise various per pixel information of the scene. So our first step is going to be actually allocating and setting up that with our frame buffer class. So here we see everything's rendering again, just unfortunately, no particles, but every problem has a fix. So let's go into here and let's change our main buffer to be called gbuffer. And then let's add a new frame buffer as well. This one we can call deferred composite. And what this one will do is it'll essentially hold the scene with light. It'll be where we draw when we're reading from the gbuffer. So the deferred composite the deferred composite frame buffer will hold our scene as it is with shadows and with the directional light applied. And then that will be the input for bloom moving forward into the rest of the rendering pipeline. So let's go into game.cpp and let's initialize these guys up. So main buffer over here, or let's start at the very top actually. So main buffer doesn't exist anymore, and we're going to create gbuffer instead. That one is actually going to have the most we've used yet. It's going to have 3 color buffers, and you'll see what they're all going to be used for momentarily. Let's also initialize our new deferred composite. That's going to have just 1 color buffer. So let's move down. Main buffer can change into gbuffer. Change them here as well. So now this is going to have a bunch more in it. So this guy here, the first buffer we're going to add onto it is going to be our flat color. That's what's going to be written to that slot. So flat color meaning just the straight up texture color that was red for the pixel that fell into that spot. So it's not going to have anything done to it. It's essentially going to be a pass-through as far as that texture slot is concerned. Now, I should mention that we do want a depth texture here, of course, because we are going to be rendering geometry to our gbuffer, so we want to make sure that things that are in front of each other will in fact appear in front of them. So, second one, right, slot 1, it's going to have the exact same data format, except or it's going to have the exact same parameters, except the data format is going to be different here in the middle. And we're only going to need 3 channels because this one is going to hold normals. And of course, those are XYZ vectors, and they do not require a 4th component, so we might as well save the memory there. And the last buffer, the 3rd one, is going to be actually kind of cool. So for this one, we're going to have 3 channels because we're going to specify view space positions. This buffer is actually, for every single pixel, going to specify where the position of a triangle was, of a point in space, right? A pixel, a fragment, where that fragment was relative to the camera, if the camera was 0, 0, 0. So, as you might remember, we were talking about packing normals into a texture, and we were talking about how we would have to pack and unpack them because of the fact that regular OpenGL textures and frame buffer textures enforce that things written to them must be within the range of 0 to 1, because that's what color is, right? They're built primarily for color, and so there's nothing the screen knows how to display other than something between the range of 0 to 1. If it's 0, 0, 0, then it's black. If it's 1, 1, 1, then it's pure white. So you can't have anything negative, right? It wouldn't make sense. So if you try to put something negative into it, it'll actually get clamped to 0, 0, 0. If you try to put 2, 2, 2 in there, it'll get clamped to 1, 1, 1. So that proposes a bit of a problem because view space positions could literally be anything, right? We could be looking at something in the distance that's thousands of units away. There's units, if you think about the camera as being the origin, then to our bottom left quadrant of the screen, everything's going to be negative. So we're going to need some sort of solution for this last buffer. And it's not going to be trivial to pack something that has so much potential range into 0 to 1. So what we're going to do instead is we're going to specify a data format of RGB, and it's going to be 32 bits per channel, and they're going to be floats. So this texture is actually going to relax the restrictions, and it's going to allow us to write the floats of view space position directly to this texture without having to conform them to that 0 to 1 range, whereas the other two will. And we'll see that in the shader, but I just wanted to mention it now. So let's move on and also make our new deferred composite buffer. So we're going to want one color texture on here. We're not going to need depth for this guy. Let's have our window width as well here. Then I can just copy this block. Well, actually, I need to edit the color texture too. Oops, I should say height. Oh, what am I doing? I'm getting confused. I'm trying to copy that with my eyes while I'm actually editing a color texture. So what is this going to be? It's going to be a full screen buffer, right? It's going to be used mainly for other post-processing passes to read from. We could get away with leaving it as just a 3-channel texture, but in case you want to do anything fancy, I'll leave it as a 4-channel texture for you. And then we're going to have nearest sampling. We don't want any blurring to go on, and above that we don't expect to be rendering to anything other than the exact size of the screen, so nearest sampling is fine. And with that, oh, what's it missing here? Too few arguments. I think that might just be IntelliSense. Oh, sorry, forgot the index. No, there we go, my mistake. So there we go, second buffer done and done. Now let's go ahead and actually use these guys. So here at the bottom, immediately we're going to see that main buffer no longer exists, so we're going to need to clear that guy. And we're going to shimmy these things around a little bit today. So first, let's get rid of this error by changing this to gbuffer. Gbuffer, however, is not going to want the clear color of the sky. Gbuffer is more of a utility buffer that's going to hold positions and normals and things like that, so we don't want to start it off by being a sky color. That won't make sense for the buffers that represent normals and positions. So let's move this line down underneath the clear color for black. What we're going to want now as the target for our sky color clearing is our deferred composite, where our actual scene will be rendered to. And so we'll leave that as the sky color. So let's go down to where the scene is being generated, and of course we'll find that main buffer again is no longer valid. So we can change the bind and unbind for that guy, and the rest will stay the same. The only problem is, how are we going to actually write to those locations, right? This is a good place to stop and make sure that our what we've done so far works. But we are missing the shader, right? The shader is going to be the key that distributes the outputs to each of those three buffers, and we've never done that before, but today we will. We're going to have a shader that actually outputs to multiple locations at the same time. So I am going to comment out the rest of the render function up until swap buffers. Of course, we still want that guy in there. And so all our bloom stuff is gone. Oh, my mistake. I meant to go up to here from the high pass. And we just go up until rendering our scene. We still have this the shadow map generation up above this. So what we're going to need now is we're going to need a new shader to replace this static geometry one that we were using previously. So let's go into our header, new shader program. We can call it, looks like we have bloom high pass there. Let's call this gbuffer pass. Let's bring this guy over to game.cpp and let's find some more shaders. Here's some more shaders. Copy one of these blocks. Replace this with gbuffer pass. And now, what are we going to want for this guy? Well, he's going to be, gbuffer pass is going to be rendering geometry. So we want a capable vertex shader. So we're going to want to grab static geometry.vert. We're going to be using that in here to load our, to process our vertices. But we're going to need that special fragment shader now. So let's go write that. If we jump into our framework, go into our shaders, let's create a new one, right? New text document. Let's call it gbuffer pass.frag. Now we'll take that and we'll add it to our shaders in Visual Studio. Gbuffer pass. Let's get started. So version 420 to match our OpenGL. What are we gonna need inside here? Well, we're rendering objects. We're rendering them rather simply. We're gonna need their texture first of all. We know this is going to link up to our static geometry.vert, so we know our inputs from the vertex shader are going to be our vec2 texture coordinate, as well as our vec3 normal in view space, and our vec3 position. Now normally what we would have for a fragment shader like this is we would have an out vec for out color, and then we'd start our main function. Now things are a little bit different now, right? We have to somehow specify more outputs. So As you might expect, it would look something like this. Vec3, well, we're going to want to output our normals as well. And another Vec3, we're going to want to output our view space position. Now the problem is, how does OpenGL know which one of these we want to go to which respective texture in our FBO? And of course it doesn't, so we have to specify. So as the programmer, we know what we intend slot 0 to be, slot 1 to be, and slot 2 to be. And very similar to how our inputs work and how we specify where we want VBOs to feed in to a vertex shader, we can specify how we want the fragment shader to write to multiple locations. So we're going to specify behind all of these layout, location equals, and of course we'll have 0 for the first one, 1 for the second one, and 2 for position, which of course matches up with our buffers the way we've set them up. So let's do that. Let's pass through our data. We have everything we need here in order to write to each of these individual buffers. So let's get our standard color output, right? Pretty much a pass through, and that's going to be written to outColor dot RGB is equal to texture. Going to read from uText. We're going to write. We're going to have text coord be our coordinate. For simplicity, I'm going to set the alpha equal to 1. Now, what about our normals? We have to pack those, right? So our out normal is going to be equal to our incoming normal multiplied by 0.5 plus 0.5. So keep in mind, our incoming normals, every single channel is within the range of -1 to 1, because of course the normal must be able to point in any direction in space. But our out, we intend to be 0 to 1. And so, as we talked about many times, we perform that linear conversion of space. There is another catch though. Remember that this normal here coming in from the vertex shader has been passed through the rasterizer, which does not guarantee that the length of the normal is intact. So we're going to want to normalize that sucker, and then we're good to go. Lastly, we have our positions, our view space positions, I should say. Now, the nice thing about the float textures, as we mentioned, is we can write directly to it. Doesn't need to be packed. It can fully represent a float with no problem. No need to pack. Awesome. So that is our fragment shader for the gbuffer. Let's finish uploading it in and getting it set up. So if we go to our gbuffer pass here, we can now change the name of the fragment shader to be just shaders gbuffer pass. And now I'm going to want to be binding this guy when our scene is being rendered. If I go down, compute shadow map can use the static geometry shader. That's absolutely fine. But for generating the scene, I'm going to want to change all of these to gbuffer pass. Along with the unbind here for readability, I'm going to set to gbuffer pass as well. So if we render this, we shouldn't see anything because, of course, everything is being sent to frame buffers. Nothing's being sent to the back buffer. But let's check for errors, of course, like we see here. And then let's take a look through Nsight and dissect this gbuffer. So fragment shader failed to compile, unidentified variable out normal. So what did I do? Out normals. Oh, whoops. Out normal. There we go. Anything else? Doesn't look like it. If we don't get a black screen, I'll be thoroughly surprised. There we go. Let's run it through Nsight now. And let's see how you would observe such a situation, such a rendering pipeline in Nsight, and how we can double check our work. So here we go. So stuff is definitely rendering. We're using our shaders. Let's pause. Oh, stuff is coming up. That's nice. If we go back to this block, we can expect to view the shadow map coming up. But if we go here, okay, it looks like the color's coming up, right? But where's the rest of our data? Well, you have to use Insight to examine every single write buffer individually, right? So right now, if we click on this here, which views your render targets, we're viewing render target 0, which we specified for our flat colors. If we switch to render target 1, we can see that we're in fact observing the normals in view space, and of course that is again why the ground is green and the parts of the planks that are pointing upwards are green. Parts that are pointing towards us are relatively blue because they're pointing in the positive z-axis. Here we have a little bit of red since it's pointing kind of to the right. Now of course these are packed normals, but more or less they do still tend to follow that logic with the color. If we go to the last buffer, we'll see something really cool, our view space positions. And now at first this might look like it's actually not working, but if you think about it, this is exactly what you should expect. The origin of the camera is right in the center of our eye, so as we look down the center, we find this kind of crossroads, and it exists because of the 4 quadrants. So if we think about the bottom left-hand corner, you have negative x coordinates and negative y coordinates. The GPU doesn't know how to render that as color. The screen can't do it. The values in the texture are absolutely there, and they are correct. You just can't represent them on screen, so that's why we're seeing something so strange. Up here we have negative x values, so we don't see any red on the first channel, but we do see some green. Over here we have red and green, so we're picking up yellows. And here we have just the reds. And notice as well how we have these small gradients as each of these values move between the range of 0 to 1. So here we have G of 0, and then slowly moving up to a G value or a Y value of 1. But then after that, it doesn't know how to express additional values, so it just becomes solid green. So this is absolutely correct. So, of course, we want to use this in order to build the scene as we had it before. So if we go into our big shader, our Phong directional shader, we're going to have to modify this shader in order to accept a lot of inputs from textures rather than from the vertex shader. So let's do exactly that. So if we start at the top of Phong directional, going to move down and we're going to add some new samplers. So we're going to have a sampler 2D to read the normals. So I'm going to call it a normal map, and of course normals are no longer going to be coming in from the vertex shader, right? This is going to be rendered as a full screen quad, so we're not going to be pushing through that geometry that's going to give us access to these two values. So we can delete them. All we're going to have is the texture coordinates from the full screen quad. We're going to need another map as well, our sampler 2D for our positional map. Now, before we go any further, I'd like to actually rename this file. So let's close it here. I'm going to right-click and exclude it from project in the Solution Explorer. I don't want to remove it because that'll essentially delete the file. So if I go into shaders, it's still here. I'm going to rename this to Deferred. Oh, too many R's. Deferred lighting. There we go. And then let's go and add this back in. Existing item, deferred lighting. Let's open that sucker up. All right. So let's reorganize this a little bit. In order to be a little bit more clear, we're going to get as much data as we can right at the beginning. So our texture color for the scene, oh, and I should say this wouldn't be uText anymore, but rather uScene, right? It's not the texture of a particular object, but we're reading in the entire texture that was the flat colored scene. So let's get, for this particular pixel, the data that we need. So let's have a texture color variable, and we're going to read from texture use scene text coord. It's one down. Let's get our normal, right? We're going to be reading all this data from the same respective fragment, the same pixel, so that it will be the data, the normal, the position, the color that correspond to the exact same location on the screen. So that texture coordinate is going to be very important that we use properly. Let's get our normal map. I'm going to use XYZ this time. It's a little bit more descriptive for normals. Now to unpack it, I'm going to multiply by 2 and subtract by 1. Should be self-explanatory at this point. Then let's get our view space position. We're going to take our U position map at the texture coordinate dot XYZ. We don't need to process those at all. But notice how nice it is that despite the fact that these textures have different formats, we can read from them using the exact same syntax. That's convenient. So now the rest of this shader is actually just going to work because this logic doesn't change, right? It's all the same. This is using, actually this I should take out. That doesn't need to happen anymore. The normal is now being read in by us, and it's already normalized. So we define the normal up there. So with exception to that little thing I almost forgot, nothing here has to change. It's all the same. We have our shadow mapping, that's fine. Our shadow map is already linked in. Our position is already being written to from here. So the rest of the code doesn't care because all the values are the same. The only difference is they got read in from textures rather than passed in from the vertex shader. So this is a very flexible system. Let's put this to use. Let's write to the back buffer and let's see what our scene looks like. So we're going to go into game.h and let's add a new shader program. Let's add deferred lighting. Nope. Deferred lighting is going to be what composites the G buffer into an image that resembles more what we want to see at the end of the day. So I'm going to copy one of these blocks here. Our deferred composite is now going to be pass through vertex because it's going to be a post-process. Oh, sorry, not deferred composite. Deferred lighting. That's the shader. It's going to be the pass-through, and we're going to read from the deferred lighting file to get the fragment shader. So let's go down, and after we generate, where's our G buffer? Shadow map. Generate scene, here we go. Right, so we have our high pass, but we're going to do something new this time before our high pass starts. So what we're going to do is create scene from gbuffer. And then that will get passed forward into the bloom. So let's set our viewport 0, 0, window width, window height. Let's bind our new deferred lighting shader, and we're going to need to set a whole lot of properties for this one. Now if we go up here, we can actually steal most of them from this guy. Now I didn't mention earlier, but gbuffer, the gbuffer pass doesn't need a lot of this stuff, right? Because it doesn't even do shadow mapping. It doesn't even use lights. So we can remove a bunch of this. Let's let's steal it. Let's bring it down here. Right, we're programmers, we're lazy, we can copy paste if we're careful. So let's bring these guys in. Right, here we go. It's a post process, so we're not going to need any matrices. But let's double check that we have the right variable names here. So we're going to want our U texture as our one texture, and it's going to be 0. Then, oh, what am I talking about? This is the wrong shader. What am I looking at? I want to be looking at this guy. I thought this guy was open. There we go. So here we go. Here's the ones that we need, right? I was wondering why there was just one. So we're going to need to bind our scene, our shadow map, normal map, position map, and we're going to need to send these variables. So we're already sending some of them here, right? Let's set up all the textures. Let's do, we have how many? 4, right? Yeah. So we have our U scene as our first one. Then we'll have our U shadow map. Whoops, I said first, but I meant 0, of course. Shadow map. Then we have our normal map as number 2, and lastly we'll have our position map as 3. We send our view to shadow map just as we did before. Our light direction doesn't change. None of this other stuff changes. For shader bound, we can go ahead and bind the frame buffer itself, the composite deferred map. Then it just becomes a monkey game of binding all the shaders. So let's go. First one's first, our scene goes into slot 0. So we're going to bind texture GL texture 2D, and we're going to get our gbuffer dot get color handle number 0 is going to be our scene. Then we're going to switch the active texture to texture 1. We're going to bind another texture into here. That's going to be the shadow map. So I'm going to still want the gbuffer, or sorry, I'm going to want the shadow map, and I'm going to call get depth handle this time. Of course, I want the shadow map, the depth buffer from the light's point of view, not from the camera's point of view that we're actually using to view the scene. So let's bring this guy here into slot 2. We're going to bind our normal map. That's going to be, if I copy this guy into here, that's going to be color slot 1. And lastly, we're going to need to bind our positional map, which is the last slot, slot number 2 in our gbuffer. After that, we can finally call our draw full screen quad function, which will take all our maps together and composite it into the proper scene, essentially deferring our lighting calculations until after the geometry has all been pushed through. Hence, of course, the name of deferred lighting. So now it just becomes a game of unbinding all these textures from texture 2D. So we're going to call GL none. Whoops. Then we're going to switch active texture down to 2, right? This one was called while number 3 was still active. Now we're going to want to active texture 2. Gonna unbind that one. GL active texture GL texture 1. And then finally texture 0. Once that's done, we can additionally unbind our FBO as well as our deferred lighting shader. So now if we run the program, we will still not observe anything, or we'll get errors. Let's find out. Texture color conflicts with previous declaration. I remember that one. So let's do one at a time. Fragment shader 44, this guy. So I defined texture color here, yet Oh, look at that, I lied yet again. There's this line we needed to remove as well, right? The texture color was now coming from our scene map here. So that can be removed. And let's see if we get anything else. Swizzle mask not present in operand A56. Line 56, out color equals texture color dot A. Well, texture color doesn't have A anymore. Let's just pull our usual safe bet of setting it to 1. Shader file not found. Fong directional, that's no longer being used. So instead of that, we can pretty much substitute that one for any other. And we can do that because we know static geometry is used only on the shadow map. And the shadow map doesn't even have any frame buffer color textures to write to. So the fragment shader that we supply in here will really be irrelevant. It won't be able to write anything. So with that, we should be okay to go. Pause the frame. So everything's being rendered to here. If we go to here, strangely enough, we see black again, so something's going on, but we can see that correctly all our textures here are bound, and in fact there's 4 of them. This one's being bound to slot 0, shadow map to slot 1, this one to slot 2, and this one to slot 3. So let's try and find out what's going on. Hey guys, I'm back. So I've grossly underestimated how tired I am right now, hence all of these ridiculous derps I'm having. So I forgot to, when copy pasting, probably comically after I said that we can copy paste if we're careful, forgot to change all of these G buffer names to deferred lighting names, of course. So it's no wonder that our composite pass wouldn't be rendering anything if in fact our shader wasn't able to read any of the values. So let's recompile this before we launch it through to EndSight. Of course, everything will still become black on the back buffer, but we should be able to observe. Perfect. Our scene here in the background. And indeed, it looks exactly as it would have if we used a forward renderer. But now we have the added benefit of shading only the pixels that we can see and being able to more easily reuse some of these buffers for other shader effects in order to gain a performance improvement overall. So let's push the rest of this through the bloom that we know works, and we'll be able to observe the scene exactly as it was before. So we're going to need to change a few other things here after I've uncommented the high pass. So the main buffer no longer exists. What the high pass wants, of course, is the actual scene, and that's going to be in the new composite. If we go down to the bottom once again, for the bloom to composite, it's going to want the scene and the bloom map, which will have been written to work buffer 1. So we just change main buffer to deferred composite, and we can give it a run and see our scene. Awesome. So there we go. Can't even tell that it wouldn't be a deferred renderer. Again, only being a little choppy because I have my recording software on. We're just going to add two other things to this, and then we'll be done for the day. So the first one is a check to make sure we don't shade incorrect locations. Let's take a look at EndSight one more time. So when the full screen quad is being rendered on the pass that takes together the G buffer, notice how with my animated wireframe on here you can clearly see that there are in fact 2 polygons covering the whole screen. So of course that'll generate fragment shader executions on every single pixel on the screen. So that means pixels like over here are going to be picking up all the color they need. They're going to be getting performing the lighting calculations. And then they're going to be writing the color that we expect. However, you have to consider that pixels are also being run in the background here, where we don't really want to be adding any color whatsoever. And if we were to try to apply these fragment shaders on the background, we might get weird effects, especially if the background is colored more intensely. So there's a quick fix for that, and let's implement that in here. So we know that the G buffer is cleared to all black, and that includes all the maps inside the G buffer. So that includes the scene, the normal map, and the positional map. So we can do a check. We can check if the position of this fragment we're trying to shade is 0, then that would mean that we're on a fragment that doesn't actually make sense. It must be on the background. Nothing was rendered here to give it a proper position. You can imagine a position of 0 wouldn't make any sense to begin with. It's guaranteed not to make sense because it would be a position on the camera itself. But we know that rendering only starts after the near plane, which is usually at a position of 1 on the Z. So there's no way that a position can be 0 unless, of course, it hasn't been drawn to. So let's check that. So if the length of position is equal to 0, we're going to, whoa, what is this? I just enabled some really weird cursor I've never seen before. So if the position is 0, we're going to call a GLSL keyword called discard, which tosses this fragment and prevents it from writing anything to the frame buffer, and only this fragment, right? So on a pixel per by pixel basis. So with that, we have the extra check. And the last thing I want to do today is I want to implement a quality improvement that is also a little bit of a performance hack. So what I want to ask you is, or actually, let me just show you. Let me go to the lighting here, and let me turn the specular way up. I think showing is the best way to describe this issue. So I'm going to want you to take a look at the shadows. And I'm going to want you to observe the specular highlight here moving across the shadows. Now ask yourself, does that make any sense? Well, it shouldn't, right? If an area is in shadow, that means there's no direct bounce from that position to the light. The light can't see it. So then how could we have a specular reflection on it? We can't, right? There's no way that the light would be hitting that point to then bounce into our eye. So somehow we should be able to remove that. And in fact, we can very easily. We have a first check here, which determines whether or not the surface is facing the light. And if it is, then it's going to pick up diffuse and specular, both of which are dependent on having, of course, a direct view of the light. However, if we're in shadow, then we know that that isn't possible. So let's cut our shadow code off from here, and let's move it above here. I'm going to move this comment trailing and make it trailing after the if statement. So let's put these two if statements together, and I'm going to have this part as an else if. So what's going to happen here is we're first going to determine if we're in shadow, and let's go through each case. So let's say we're in shadow. Okay, this happens. Nothing else happens. And so the only light we picked up is the ambient, which is perfect. That makes more sense. Let's say we're not in shadow. Okay, we're not in shadow, so we're probably away from the HUD. Then we can check this. Okay, we also have view of the light. Let's calculate the diffuse and the specular. So now we're going to run into some code that looks a lot more realistic. And I noticed that after adding this change, something about the scene just seemed to change. I just couldn't put my finger on it, but it just felt better. And of course, with this over-the-top specular, we can now see how it goes in between the shadows. but it doesn't actually bounce through them. So let's bring that back down. Let's bring it back down to maybe 0.1. We don't need such an intense specular. But if we run it again, now all the areas in shadow will look a little better. So, just a simple play with the if statements leads to a more realistic scene. And we can see the shadows feel a lot darker. By playing with your ambient light, if it was a more moody scene with a lot more blues, then these shadowed areas would only be picking up the ambient light, and they would really feel like they were part of that scene, although in this case we just kind of have a white and black going on. So I'm going to leave you with that for today. This framework now with the G-buffer is going to be a lot easier for us to build on top of, because we're going to have that full screen normal map and that full screen positional map, which is going to help us a lot with some of the other shader effects we're going to be doing, like the one next week with tune shading. We'll see how that works. So have a nice week. Have a nice weekend. I'll see you guys next week.